So this is the beginning of chapter 13. I highly recommend reading this. It's really interesting. It's kind of inspiring. Well, not kind of. It actually is inspiring. And it's about a boy who didn't have any education, wasn't able to go to school, but yet changed his whole entire community by having perseverance. And it has to do with building windmills, and he ended up going into, afterwards, going into environmental science. So it's kind of a really neat story. So I suggest reading that opening there. So if we look at Module 37, at the bottom here on page 453, this section is just about our renewable energy, but it starts off with conservation and efficiency. So basically, how are energy conservation and efficiency different? So how does, if we're conserving energy, how is that different from efficiency? So conserving energy would be using less, whereas efficiency would be having maybe appliances that, we have to wash our dishes, but it uses a lot less water, or flushing the toilets, the example I gave a few months ago with water, the low-flow toilets versus standard toilets. So that would be efficiency, versus conservation would be maybe flushing the toilet less. So every couple times, maybe every, instead of every once. So that would be the difference there. And then moving on to the next page, there's this table up here on the top. So know the different ways to conserve energy. Most of it, I think, is common sense, but make sure you read through it because there might be something that you missed or that you didn't think of. But it just gives different ways on how to conserve in your home with your electrical appliances, unplugging things, not leaving lights on, that kind of thing. And that's probably the easiest way to reduce energy. So yes, we want to get away from non-renewable resources and go into renewable resources, but we have to conserve. So it's not just about using lots of a different kind of energy. It's about using less and a different kind. And then moving down, why is tiered rate system used? So what exactly is a tiered rate system? Well, PG&E uses it. City of Reading, I don't think, not that I know of, they don't use that. But PG&E definitely does. Bella Vista Water does. And so basically, it's a system to kind of force you into conservation. So you get a certain amount of energy or water at a base rate. And then once you move beyond that, once you've used more than your allotment at the base rate, then your charges go up to the next level. And then if you use more than that, then it goes up to the next level, if there is one. And so it's kind of a pricing tier system in order to kind of make you do conservation. So know what the benefit would be. I kind of just explained that. Then at the bottom here, the first and second law of thermodynamics. So first law isn't really mentioned in here, but the first law is that energy is neither created or destroyed, it's conserved. So it doesn't just disappear or be created, but it's changed from one form to the other. So it might be changed from water, like for example at the dam, water is going over the dam by gravity, or through the dam, and then it goes down into the turbine, turns a turbine, which in turn generates electricity into the generator. And so that is exchange. It's moved from gravitational energy into rotational energy into electrical. So it's not lost, and it's not, it's not disappearing and it's not created, but it's conserved. The second law states that as energy transfer occurs, some is lost in the sense of like heat, for example. So when something turns, if you're turning a turbine, there's going to be heat generated. And that heat is not something that we want. Just like when we eat, we want to, our body processes take some of that energy. And, when we move up the trophic levels, only 10% or so is moved up to the next level. So it's one of the reasons when we talked about the biomes and biotic systems that at the different levels you've got your producers, there's lots of them, And then as you move up into consumers, there's less and less at each level because there's less and less energy at each level. And that has a lot to do with that second law of thermodynamics. So just make sure you understand both. And then moving to 455, how does a passive solar design aid in sustainability? So what is a passive solar design, and how does that aid in sustainability? So how does that aid in conserving energy and using as little as we can? So on the next page, they do show kind of a picture of that. So this is an example of building a house so that you maximize the amount of energy coming in during the winter versus summer. So think about Reading, for example. In the winter, it would be nice to have the sun shining through your windows in order to warm your house. Well, in the summertime, that's the last thing you want. So this house is designed so that the sun, because of the Earth's tilt, is lower in the sky in the winter than it is in the summer. And so because of the angle of this roof and where the windows are positioned, then the sun is shining in the winter, but in the summer it's hitting the roof. And so it's no longer directly shining in, or at least most of the day. And this might be a north-facing house or something like that. But it's maximizing that, so it's using passive energy. So they're not actively doing, there's no solar cells, there's nothing going on here, besides just positioning of the house. So that would be passive. And then up here it shows some things that we can do, as far as orientating your house towards the sun, so that you don't have the sun shining through your windows all the time. And like I said, that's the last thing that you want in Reading. And then they've got shade tree here in the west where the sun is setting. It tends to be warmer in the afternoon, so the sun is, the tree is shading that. And then they've got proper insulation. They're using a skylight for energy, so just a variety of things there. And that's just showing an energy-efficient home. And then on this side, this shows, it's kind of a neat picture. I don't know if you guys have been to the Academy of Sciences in San Francisco, but they do have this building there. It's pretty neat. You can go up on the roof and check out their green roof. So it's planted, so it's not using tiles or anything like that. And it's living. And so it's watered sometimes by gray water, depending on how much precipitation you get in the year. It could be watered using gray water. It could be water just from precipitation alone. But what it's doing is it's, one, insulating the building. It's helping to keep it cool because the energy is just not hitting the roof and being absorbed, but the energy is being photosynthesized. So the plants are utilizing it. The roof is not getting as hot. They're able to keep it insulated. So there's a variety of reasons to do it. Plus, it's aesthetic. Looks nice. So down here, I put on this one, benefit and drawbacks of a green roof. So there was lots of benefits I listed. A big drawback would be that it's pretty heavy. You may have pests. You may have to water it. So those might be some drawbacks, but there's quite a few benefits. And then how does thermal mass help with energy consumption in a building? So does it matter what we build a building out of? What if it's dark versus light material? What if it's cement versus wood? There's a big difference. So thermal mass is how does it absorb energy and how does it retain energy? So think about in the summer. You're walking along the ground and you walk on cement. So the cement is pretty hot, even at night. So after the sun sets, the cement retains its heat for quite a while, whereas the grass doesn't. So the grass cools down pretty fast. So thermal mass is much different in those two materials. So how would that matter in a building? How would it matter for the sides of the building? How would it matter for the roofing material? Things like that. So how does that help with energy consumption? Okay, and then on page 458, it shows up here in this table non-renewable resources, potentially renewable, and non-depletable. So non-renewable, we mentioned, those are just, we're going to use them up faster than they are being replenished. They take millions of years to replenish, and we are going to run out in the next 100 years. So, so definitely non-renewable. But these ones potentially renewable. So what does potentially renewable mean? Well, potentially renewable would be we could run out. So if we cut down more forest than is being replanted or can grow in time, then we no longer have wood as a renewable resource. Same thing with biofuel. Biofuel is made from, it's like ethanol, corn, it's made plant-based. So if we switch to biofuel, strictly biofuel, and get away from petroleum, then we can't grow enough crops in order to supply biofuel to all vehicles. So that would then make that a non-renewable resource. And, so that's kind of some of the reasons why that could be potentially renewable or non-renewable. And then non-depletable means that we will never run out. So these 4 items, we will never run out as long as humans are here on Earth. So if we run out of any of these things, then humans wouldn't be able to survive on Earth, so it wouldn't matter. But they are essentially, in the lifespan of humans on Earth, non-depletable. So this sticky note says, what does potentially renewable depend on? Well, we talked about that. And then, can we run out of non-depletable resources? Well, yes, we can. We cannot run out of non-depletable resources because they're non-depletable, and humans would not be able to survive here without them. And then the last part, this diagram, know how much energy comes from each energy source. So the top figure is the global energy use, the bottom figure is energy in the U.S. So there's a little bit of difference, but I want you guys to look and know. You don't have to memorize the percentages, but you should have an idea. You should be able to talk about the fact that most of our energy comes from non-renewable, 90%. Our renewable energy is about 10%, and then it breaks it down. So this percentage here is broken down, and you can see biomass is the majority of it, so 46%. And that's burning stuff. If you went to Wheelabrator with us, then you saw some of that production. Even though you're burning, it's fairly clean, unless you're burning in a wood-burning stove or burning out in the forest. Wheelabrator scrubs the air that's coming out of it, and so what that means is we learned that they use anhydrous ammonium, and they mix that with the exhaust in the furnace, and so that pulls out all of the nitrous oxide, all of the sulfur dioxide, all the things that are in the air, and it precipitates them into fertilizer. And then they collect that fertilizer, Haas comes, and they use that. So I thought that was pretty interesting about Wheelabrator. So not all biomass is good or bad. So if you're a wood-burning stove, you've got a fireplace, you're burning outside, those things do cause pollution because there's nothing collecting that gases that are going into the air. So that can be both good and bad. And then hydroelectric in the U.S., we've tapped out as far as the amount of hydroelectric that we can make, unless we raise the dam, they've talked about, or things like that. But we've pretty much put all the dams that we can in the U.S. On the rivers, so that's probably not going to increase. Wind and solar probably will. So those two I would expect would increase dramatically. Geothermal is using the heat in the earth. That's probably not going to change too much, I wouldn't imagine. But solar and wind are probably going to increase quite a bit if we compare these numbers to maybe 10 years from now, or even maybe 5 years from now. So just basically kind of have an understanding of which is the most, which is the least, and how that might change in the future. Okay, and that is M37.